Welcome to AI for Good, the leading United Nations platform on artificial intelligence. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with over 50 UN agencies, and co-convened with Switzerland. The mission of AI for Good is to unlock AI's potential to serve humanity. As a multi-stakeholder platform, AI for Good advances solutions, standards, and skills. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging session. Boost your AI skills and elevate your career with the AI for Good Discovery Badge. Receive verified digital credentials that recognize your engagement in cutting-edge sessions, exploring how AI is being used to tackle global challenges. To see if a session is eligible, look for the blue badge banner on the right side of the video interface that activates at the end of each live session. Share your badge on LinkedIn and across your professional profiles, and check the AI for Good events webpage for upcoming eligible online sessions. Discovery Badge sessions are part of the AI Skills Coalition, ITU's global initiative to strengthen credible AI learning pathways and expand access to high-quality, trustworthy AI knowledge worldwide. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good afternoon, everyone, and welcome to this meeting. I'm Dominique Burgess from Orange, a leading French multinational telecommunications operator, but here I'm also chair of the ITU Standards Group on the Environment, Electronic Magnetic Fields, Climate Action, and Circular Economy. ITU, the International Telecommunication Union, is a specialized agency from the United Systems, and its work is based around three pillars: the development, the radio frequencies, and the standardization one. Study Group 5 is part of the standardization activity, of course. It is a pleasure to open the first session of the Discovery series on environmentally sustainable AI, and I would like to warmly thank all participants joining us today from around the world. This new series aims to explore emerging research, technologies, and approaches that can help ensure that the development of AI is aligned with environmental sustainability objectives. Artificial intelligence is rapidly growing and transforming our economies and societies. From healthcare to transportation, energy systems to communications network, AI is becoming a key driver of innovations and digital transformation. At the same time, it is essential that these transformations take place in a sustainable manner. As AI systems continue to scale, questions related to energy consumption, resource use, and the broader environmental footprint of AI technologies are becoming increasingly important. This topic has been particularly visible in international discussions over the past weeks. Just 2 weeks ago, for example, during the AI Indian Summit, the environmental sustainability of AI was highlighted as a key issue requiring global cooperation across research, industry, and policy communities. In parallel, the Coalition for Sustainable AI, together with ITU, ISO, and IEEE, recently launched the Global Approach to Standardization for AI Environmental Sustainability, aiming to strengthen coordination among standards organizations and provide a current framework for measuring and addressing the environmental impacts of AI systems. We as ITU participate actively in this work, which helps present the state of art of all approved and ongoing work on sustainable AI in relevant standard development organizations. Within ITU, as I mentioned, the work is carried within Study Group 5. In February this year, the group did approve a very important recommendation, which is maybe the first among all standard development organizations, which is called in our language Recommendation ITU L.1801, recommendation is the name within ITU for the standard, so we can say has approved the new standards addressing the guidelines for assessing the environmental impact of artificial intelligence systems. This landmark standards provides a holistic framework to evaluate the environmental impact of AI, covering both direct and indirect effects and offering guidance on how these impacts can be assessed and mitigated. This recommendation, of course, is not totally new because on the principle it has been inspired by previous methodologies we did develop, in particular the standards, the recommendation L.1410, which provides a framework for environmental life cycle assessment of ICT goods, network and services, and also another famous one, which is a standard called L.1480, which assesses how ICT solutions can enable greenhouse gas emissions reductions in other sectors and support the net zero transition. By combining these approaches, these standards, L.1801 enables the assessment of the full life cycle of AI systems, allowing comparative evaluations, for example, between AI-enabled and non-AI approaches or between different AI systems. In addition to this work on the environmental impact of AI, Study Group 5 is also advancing standards to improve the sustainability of the digital infrastructures that support AI, including work on energy efficient data centers and the energy efficiency of telecommunication networks, as well as methodologies supporting climate actions across the ICT sector. This week, the Mobile World Congress is taking place in Barcelona, and here also the AI has been placed at the center of global discussions. Along the tremendous opportunities of AI, its environmental footprints, including increasing demand for energy, water, and materials across the digital infrastructures that support AI, is becoming an important part of discussion. It is also important to recognize that AI itself can support environmental sustainability, helping optimize energy systems, improve climate modeling, support biodiversity monitoring, and enable more efficient resources management. Within ITU, we explore these opportunities through other initiatives and discovery series dedicated to AI for the environment. However, this discovery series on environmental sustainability AI focus especially on another crucial dimension, that is understanding and addressing the environmental impact of AI technologies themselves. The objective of this series is to bring together scientific research, industry innovation, policy perspectives, and standardization activities, helping us better understand how AI systems can evolve in a way that is both powerful and environmentally responsible. I'm particularly pleased that this series is being co-curated together with Professor Gita Kitinyuk, Bavarian AI Chair for Mathematical Foundations of Artificial Intelligence at the Ludwig Maximilians University in München, whose academic perspective helps connect cutting-edge research with developments in technology, policy, and standard. With that, I would like to thank you for all joining this first session of a series, and I have the pleasure now of handing the floor to Professor Gita Kitinyuk, who will continue the program and introduce today's speaker. Professor Gita Kitinyuk, as I said, holds the Bavarian AI Chair for the Mathematical Foundations of Artificial Intelligence. She had previously worked at the Einstein. She had previously the Einstein Chair at the TU Berlin, and her research develops next-generation AI computing from a mathematical perspective with the aim of building AI systems that are both reliable and sustainable, particularly energy efficient. Her work has received numerous distinctions. I will not quote all of them here, but we can mention the Kevin Prize of the DFG, and she has been elected also at the Berlin Brandenburg Academy of Science and Humanities and at the European Academy of Science. And in addition to that, today, she still continues to have several roles, and in particular, she's co-founder of the startup Ecology Computing. So, Professor Gita, I give you a floor, and thank you to all of you. Thank you very much, and wishing you a good meeting. Thank you.
Yeah, thank you so much, Dominique, for the very kind introduction. And I would also like to start by expressing my sincere gratitude to the ITU and also the AI for Good initiative for supporting and launching this environmentally sustainable AI discovery series. I think we all know that artificial intelligence is currently transforming science, industry, and society at an unprecedented pace, but at the same time, this rapid scaling of modern AI systems, which we see today, in particular in generative AI, has raised important questions about their environmental footprint. And I think here, for instance, of energy consumption, water usage for cooling infrastructure, or also the carbon footprint of large-scale computing models, which are all increasingly becoming central topics in science, also industry, and politics. And we all know that addressing all those challenges requires a truly interdisciplinary and multidisciplinary perspective to tackle questions concerning environmental sustainability of AI, in particular, for instance, concerning machine learning, computer science, mathematics, hardware engineering, infrastructure design, environmental sciences, policy, and so on. And this is precisely the motivation behind this environmentally sustainable AI discovery series. The goal of the series is to explore how AI can evolve in a way that is both powerful, but at the same time also environmentally responsible. And so in general, this series is structured around three central topics. The first topic is quantifying the problem. Before we can solve a challenge, we need to understand it. So there will be speakers in this series which will discuss environmental and empirical data on aspects like research usage of modern AI systems. And also at the same time, we will discuss which metrics already exist and which additional indicators may be needed to enable robust measurements and meaningful comparison across AI systems. The second topic is then engineering a solution for that. Sustainable AI will require technological innovation, and speakers in this series will present advances in algorithmic efficiency, model design, software optimization, but at the same time, we will also explore progress in hardware and infrastructure, like, for instance, low power computing infrastructure, specialized AI hardware like neuromorphic computing, and also innovations in energy efficient data centers. And the third topic is guidelines and transparency. Long-term sustainable AI will ultimately also require frameworks, standards, reporting practices to increase transparency about the environmental impacts. So experts in this series will also discuss emerging initiatives in that direction, and taking together all these three perspectives, quantifying the problem, engineering a solution, and then also developing guidelines, transparency will, to my mind, form an excellent foundation for building environmentally sustainable AI. And today I'm very pleased to begin this discovery series with a particularly exciting topic, spike-based machine learning. This line of research draws inspiration from biological neural systems, explores computational principles that differ fundamentally from conventional deep learning architectures, with the goal to ultimately significantly improve the energy efficiency of AI systems. And it's my great pleasure and honor to introduce today's speaker, Professor Dr. Priya Panda. Professor Panda is the Lloyd Hunt Early Career Chair of Electrical and Computer Engineering at the University of Southern California. Prior to joining USC, she served as an assistant professor at Yale University, and for instance, she has also worked as a visiting faculty researcher at Google DeepMind. Her work focuses on algorithm hardware co-design for efficient artificial intelligence and machine learning, with a particular emphasis on neuromorphic computing and spiking neural networks. And in general, her work aims to develop AI systems that combine very strong performance with significantly improved energy efficiency. She received her PhD from Purdue University, and in general, her research has received numerous awards and recognitions. For instance, an NSF Career Award, the DARPA Riser Award, the DARPA Directors Fellowship Award, Google Research Scholar Award, and so on. In addition, many best paper awards and others. So I could continue like this, but I mean, since time is precious, I would like to stop here with, let's say, naming all the recognitions she has achieved during her career so far. I'm very pleased that we got her to open this discovery series today. Priya, thank you so very much for joining us. We are very much looking forward to your presentation. The floor is yours.
Thank you so much, Geeta, for that kind introduction. And I'm really glad to be, starting this series. So as Geeta has mentioned, we all know the limitations that AI poses today. And with the unprecedented rise in AI, where AI is trying to surround us and embed in every technology that surrounds us, there is a need to start thinking about what are the limitations, right, to make AI ubiquitous. And one of the key limitations is actually the energetics, right? So my research has been from the very beginning about how do we make AI more and more energy efficient? Meaning, can we extract more performance for the same amount of power or watt consumption? Or can you lower the power and maybe take AI to a niche application where the power needs for that particular intelligent processing would reduce? And I have been trying to use brain-inspired mechanisms, brain-inspired algorithms, brain-inspired hardware in order to see how can we bridge the gap between artificial intelligence of today and natural intelligence, which we know is one of the most efficient machines out there. So today's talk is going to focus on my work on spike-based machine intelligence, and I will take you through this whole story about, how did we derive these biological inspiration, what kind of inspirations and abstractions are possible when we actually start implementing them and deploying them on silicon, and then start taking you to, what type of efficient AI mainstream applications can we target using these biologically inspired motifs. So with that in mind, let's get started. As Geeta has already mentioned, and as we all know, I'm preaching to the choir here. We have seen some massive breakthroughs in AI since 2022, especially after the large language models came in. And generative AI is something we have all been starting to use, right? And there is a reason why the World Economic Forum in 2024 has said that, AI, especially generative AI, promises to be the steam engine of the fourth industrial revolution, because now with the capabilities that these models are giving us, we can now start putting them onto different platforms. Video generation can be used for creative tools. Putting these large language models or foundational vision language models on robots that would help you with navigation, logistics, thinking about going and looking into uncharted spaces. So all of this is becoming more and more of a reality thanks to the unprecedented scale and capabilities that AI has been able to give us. However, there are some key challenges, and the main challenge is that these models are prohibitively costly. And what does that mean? So let me give you an example here, right? So if you, let's say you're using ChatGPT, it seems that when you do 10 Q&A, I mean, when you do like 10 rounds of chat with ChatGPT, it drains almost 2% of an iPhone battery. Okay. Now, it's okay. iPhone battery, who cares? We can always charge it, right? But if you see, the amount of energy that goes into training these models before they are actually deployed, before you can start conversing with them, they actually consume a lot of energy, and that energy directly translates to carbon emissions. And today we have to be more environmentally sustainable, and we have seen today that these AI data centers are becoming a big part of the carbon emission story. So for example, again, this is just when you are doing some Q&A, that means just doing simple inference with a ChatGPT machine, and let's say 400 users at one point at a time are doing some Q&A with ChatGPT, the amount of carbon emission that server that hosts ChatGPT is emitting is equivalent to driving your a car for 1 mile, right? And this is still inference, right? That means I have already trained the model. I'm just inferring or testing the model. But if you think about training, that means how do we train the model to make it capable? Then this training can take up to carbon emissions that are equivalent to almost the lifetime emissions of 5 to 10 US cars, or even an average electricity consumption of any US household. So these are very staggering numbers, and we cannot anymore go with this kind of scaling laws where you just put in more power, you just put in more compute and expect the model to become better, which is what is happening today. But that comes at a huge cost to our environment, and we cannot do that anymore. So what we need to think about is, let's take inspiration from biology. And what is the most efficient, intelligent machine out there? It's our human brain, right? And it turns out the brain is remarkably efficient. Over millions of years of evolution, the brain has figured out a way in which for example, I'm talking to you, I'm moving my hand, I'm thinking about like what I'll speak next. All of this is happening with a very tight power budget of just 20 to 30 watts, right? And there are certain reasons why the brain is so remarkably efficient. And those are the reasons that we are trying to find in our group, and trying to see if we can take those reasons and bring in some abstractions that can bridge the gap in terms of efficiency between natural intelligence and artificial intelligence. So what are the main abstractions that we are looking at? Now, of course, a whole lot of neuroscientists and psychologists, cognitive scientists are still thinking about what makes the brain so remarkably capable. How does the learning mechanisms work? Why is it so efficient in terms of its processing? All of that is still under research. But there are a few things that we, from an engineering perspective, can take inspiration from. The first thing is that the neurons and synapses in the brain, which can be thought of as the compute and memory elements in the brain, they actually communicate and compute in the form of very sparse information, which are called spikes. And this spikes is going to become the bedrock of the computing paradigm that I'm going to be talking about, which is spiking neural networks. And the other thing is that the same neurons and synapses, which are the memory and compute elements, they're all collocated. By collocated, I mean that there is not a separate memory and a separate compute area, and then there is like a wire running between them. Everything is intermingled with each other, right? So you actually reduce a lot of communication traffic because of this collocation. So taking inspiration from these two brain-inspired motives, what we are trying to see is that if we bring in this spike-driven computation and communication in a neural network architecture, can we actually take advantage of these binary and sparse computations in order to bring in efficiency? And it turns out we can bring in efficiency, because as soon as we bring in spikes, we can actually reduce the fundamental dot product or multiply and accumulate operation to a simple accumulate operation, meaning that we will go ahead and do dot products without any multipliers, right? So this can be a huge advantage when you deploy it on hardware. And again, in the next slides, I'll show you how. The other thing to think about is, now that we have this interesting paradigm of event-driven computing, where we are working with very sparse information that is coming over time. So temporality plays a huge role in case of spiking neural networks. What type of processing unit, right, is going to give you the best benefit in terms of the hardware-software co-design? So we are thinking about, can we go all the way digital? So think about a digital TPU-like architecture, like a systolic array. Or can we go for something more exotic, where we actually take into account this co-location philosophy, right? So we actually are thinking about embedding compute and memory together, and this paradigm is called in-memory computing, and that can give you very efficient dot product computations, which will give you very high throughput. Of course, it's going to be area efficient and also give you low energy. So my research at USC and prior to that at Yale has been diving into how do we bring in or marry this algorithmic world with the hardware world, right? So just to give you a quick overview of the type of work we have done over the past couple of years, what we have been doing is with spiking neural networks, we have been trying to think about what type of algorithms can we build and what type of hardware tools can we build in order to take these models and push them for mainstream AI applications. And then evaluate on all sorts of metrics whether or not they are capable in terms of as compared to the conventional AI models. At the same time, we've been also thinking about, now that we have this interesting way of dealing with sparsity and low precision, can we do some systematic design space exploration and optimization of current AI models like the transformers, like the chat GPTs, etc., using these philosophies, and can we bring in aspects of sparsity, compression, low precision to the current AI models and make them more efficient, right? So this is all biologically derived philosophy to conventional AI in order to make it more efficient. And finally, the idea is that, one of the key application spaces where we want to push these models as and when they become more and more efficient is edge, right? Because everything works in the server because you're assuming server has unlimited power, right? But at the edge, you have limited power because most of the time you're running these edge devices on a battery, which will have constraints. So how do we drive new edge AI applications, especially for autonomous tasks, whether it is physical intelligence in robotic space or the drone space or wearable space? So these are certain things on an application side that we have been looking into. Of course, in the interest of time today, I'll be just going over some major works that we have done in the context of spiking and how that has forayed us into different application spaces, as well as what type of hardware alternatives have we thought about that give us a good match for these spiking models. So the big questions that we are trying to ask in order to do this biologically inspired co-design between software and hardware is that the first research question that we have been asking is that in spiking neural networks, we have this temporal dimension or time dimension to work with. So can we effectively leverage the time statistics that these networks offer in order to enable more capable and efficient learning? That's the first question. The second question is, what type of design space considerations do we need to have for spiking neural networks, and what type of optimizations can we do in order to really, when we actually implement them on hardware, we translate all the benefits from the algorithm onto the hardware as well. And the final thing is, what are the applications where spiking neural networks are going to set new upper bounds? By upper bounds, I mean in terms of energy efficiency targets as well as in terms of accuracy targets. And they should set new upper bounds over the traditional models, which I will call as artificial neural networks. So this requires us to think about algorithms, applications, and architectures all together and then rethink the core design space essentially. So today I thought, for the sake of this talk and for the audience, I'll be going over some basics 101 on, how are spiking neural networks different from artificial neural networks, and then try to take you through the whole story of how can they be, what type of applications can we build with them. So if you see here, in terms of an architecture, the spiking network and the artificial neural network architecture is very, very similar, right? You can have a fully connected architecture as I'm showing here, but you can go for a convolutional network, you can go for a transformer-like architecture. The only difference is that now your computations are going to be different, right? Here you're working with real values, whereas here you're working with these binary spiked streams coming in over a period of time. And that means that wherever there is this red line, that's a 1. And wherever there is no red line, that means it's a zero. So you get these ones and zeros, but like a stream of ones and zeros coming in, and you have to process this stream of ones and zeros through a neuron. So what we have to do in terms of the neuronal operation here is that you need a neuronal activation function that can account for this temporal behavior, right? So what we generally do in a spiking neural network is that we use a very popular, widely used activation function called a leaky integrated fire activation function. And the idea is that in leaky integrated fire activation function, there is this dynamical quantity called membrane potential. This membrane potential integrates or leaks in the presence or absence of these spikes. And whenever the membrane potential crosses a certain threshold, it will output a spike, which is then communicated to the rest of the network. So that's the general working of the neuronal activation for the spiking neural network. Now, what are the features, right? Or what are the advantages? The thing is that we already know with a standard artificial neural network or ANN, we know that they give you high performance. They can go for, we can apply them to various applications. But with the spiking network now, if you see, these neurons are not going to be spiking at all times. Most of the times they will not spike. And it turns out that the amount of sparsity we can get is more than 90%. So you get activation sparsity as a free lunch when you do this kind of encoding. And the other thing is that you are working with both spatial and temporal inputs because the space comes from the fact that you have this hierarchy, and the temporality comes from the fact that you're now processing information over time. So you have an extra dimension you can work with. And if you are able to leverage that dimension well, maybe it will give you some interesting statistics that can improve accuracy, robustness, efficiency, etc. So that's the key thing we want to look at going forward. Now, from a hardware perspective, right, that I'm an ECE, I'm an electrical and computer engineer, so I always think about the hardware perspective. So from a hardware perspective, why is it interesting to me? Because if you see here, in case of an ANN, you have to have these basic multiplier and accumulator operations in order to go through what we call as a dot product, right? That's a fundamental operation in a neural network. So the same fundamental operation in a spiking neural network is now, it's the same dot product, but now we don't need a multiplier. Why do we not need a multiplier? Because now the inputs are all binary, right? So a simple AND gate is going to suffice. So by replacing the multiplier, getting rid of the multiplier completely, we now, in terms of just power, let's say, you get like 30x benefit, right? So that's the reason why it's so important to think about these spiking neural networks. And this is just for one neuron. You have if you have hundreds or millions of neurons, for every neuron, you get this 30x power benefit, right? So this is the reason why people have been thinking about neuromorphic computing as a way to approach ubiquitous edge AI applications. And spiking neural networks can enable that because of their low power and multiplier-less computations. Now, however, this is all good. There's a lot of good things about spiking, but the most important bottleneck in case of spiking neural networks is that there is no good training mechanism. As I said, we are working with a very different kind of a spatio-temporal encoding paradigm. So now you cannot, what we have been using so far when you're training these standard neural networks is these backpropagation training, which requires gradient calculations. Now, gradient calculations with spiking neural networks is difficult because the way this activation function is, there's a thresholding operation, and that thresholding operation introduces a discontinuity. So you'll have a lot of non-differentiability if you calculate gradients, and that can lead to discontinuous gradients, and backpropagation may not work. So we have to have some go-arounds in order to make sure that these models are trainable. So, and that has been kind of the focus of the community over the last couple of years, that can we efficiently train spiking neural networks? And it turns out that people have come up with varied training mechanisms. They started thinking about very biologically realistic training, like spike timing dependent plasticity learning, which is a completely unsupervised local learning rule. So from a hardware perspective, very good. But the problem is that you cannot scale up. Okay. Then people started thinking about, you know what? There are so many of these models out there. I am going to take all these models and just convert them into spiking models, right? So you take a ReLU neuron and convert it to a spiking neuron, whether it is for a transformer architecture or a conv architecture, and you can do that. But the problem again is that because you're not inherently taking the temporal information and the sparsity that the standard spiking network has when you're doing this conversion, so you'll not really get the energy efficiency that you are aiming for. So what we started thinking about is, can we do some kind of back propagation in a spiking neural network? Of course, this back propagation is going to be a modified back propagation. It will be gradient descent, but with some approximations and surrogates. And it turns out that if you can do these approximations and surrogates to do this gradient-based backprop learning that leverages the time statistics, then we can start thinking about how to trade off efficiency, accuracy, and robustness altogether. And lo and behold, a lot of works have come up where people have been able to successfully show a surrogate backpropagation and approximate backpropagation training with these models. And more people have been trying to think about how to incorporate better temporal statistics during training. Okay. So one of the things I want to highlight here is one of our works from 2021, where we thought about incorporating better temporal statistics by modifying a normalization layer in a neural network. Now, these normalization layers are generally there in every architecture you find today, whether it is a conv layer or a transformer architecture. You will always have some normalization layers in between that help you balance the training of the model. And what we did was that we incorporated some internal parameters that capture the temporal propagation of spikes. Now, because this is going to a broader audience, I don't want to go into the details of how we did that. But the idea is that we started capturing temporal propagation of spikes using what we call as this batch normalization through time normalization layer. And interestingly enough, what we found out was that as soon as we did that, we saw a stark difference in the way the model started reacting or activating. So what I'm showing you here in these graphs are the spiking activity of a standard spiking neural network from different layers after it has been trained. So what you see is that with standard methods, right, what they do is what happens is that the spiking activity initially is 0, right? And over a period of time, it increases and then goes to some saturation limits, right? But whereas when we started incorporating this batch norm through time layer with the right temporal statistics, what we found out was that our information is actually like there's this Gaussian curve trend. So the spike activity increases and then decreases in a layer-wise manner. So what does that mean? This means that, your earlier layers are spiking early and the later layers are spiking later, which is what should happen. There is temporal propagation of spikes, right? So the earlier layers are spiking early, later layers are spiking later. And once their job is done, they go down, right? And that's what you want, right? So that means your earlier layers, after they have activated, then they stop, they become idle. So you can switch off the power. Right? So this is where the power and energy efficiency comes in. I'm going to skip this part. Yeah, sorry. So again, like by incorporating these temporal statistics, we were able to show that, we are actually preserving the accuracy of the model while being able to reduce the latency, which again contributes to the total energy efficiency of the model. So the energy efficiency that we got because of this, as I said, like, the temporal propagation of spikes where early layers spike early, later layers spike later. And once they have spiked, if the activity dies down, meaning they're idle, you can switch off the power to them. Because of that, we found out that, the amount of energy efficiency we get is almost, a 10x to 50x, depending upon, again, the type of model we are running. So that's a huge amount of energy efficiency to tap into. So encouraged by this result, we started foraying spiking neural networks into multitude of applications. So today we have run applications of spiking on AR, VR, which are doing object tracking. We have started pushing them for LiDAR-based detection for autonomous driving. We have pushed them into healthcare, especially where a lot of devices work with these time series, or a lot of devices give you these time series data, and then you have to learn from this time series data whether a person is about to fall down, or how a person's physical activity has been through the day, etc. And then, of course, we are also trying to push them to scientific ML for regression tasks. This is very, very important if you want to analyze weather patterns and climate changes related things. So this is a very interesting application, again, where we are pushing spiking networks. So in the case of healthcare, I want to give you an example where we were actually, the main application we were running was that we wanted to see whether a person is standing, whether a person is walking, whether a person is running, etc. And essentially today, all your smart devices, if you're wearing an iPhone watch or a Fitbit, it already gives you these decisions. So we wanted to basically replace the neural network on that device with a spiking neural network. And we wanted to see whether or not it is able to give you the right type of decision, but at, of course, much lower power consumption. So what we found out was that when we replaced this model on the device with a spiking model, we were able to get much better accuracy than, let's say, when you are using a standard model, like a recurrent model, like an LSTM. And at the same time, we were able to reduce the energy consumption by up to 94%, right? So there is almost 94, meaning almost more, like nearly half energy consumption reduction just by replacing a model with a spiking neural network. And this is the realistic application we went after. Now, the other thing, efficiency and accuracy are good, but we also want to get something more. And that more comes from robustness, right? Now, what is robustness? What is the type of robustness that I'm talking about? The robustness that I'm talking about is adversarial robustness. Now, you may have seen these pictures today in the web, where you have seen models hallucinate a lot. Or when you give some very simple noise data to an image, and the image is actually like, when you look at the image after adding the noise, to a human eye, it is imperceptible that you have even added any noise to the image. But now if you see, like, the model completely gets fooled. Earlier, it was recognizing this bird as a macaw bird with such high confidence, and now it recognizes it as a bookcase, right? With, again, almost 90% confidence. So those are all adversarial inputs which fool a model completely, but a human will never get fooled like this. So we wanted to see, like, we found out that actually spiking neural networks are actually much more robust to such kind of adversarial attacks than that of your conventional models. So we wanted to see what is the reason why we are getting this extra adversarial robustness. And it turns out that we built an interpretability tool in order to judge this robustness behavior. And the interpretability tool was again built using temporal statistics. So the way we came up with this temporal statistics interpretability tool is that for every neuron, we were seeing its spike timing behavior. So whenever a neuron was spiking with very high frequency, and the spike timings were very close to each other, we will assign that neuron some an importance score, and which will tell us that, okay, if they are spiking, if the neuron spikes are coming close to each other, that means this neuron is learning something very important. Whereas a neuron spike, if it is very sparse and it is very distant from each other, that means this neuron is probably not learning anything important. So we can assign a low importance score to that neuron. So based on this importance score that was calculated using these interspike interval, we were able to essentially build what we call as a interpretability activation map. And this interpretability map tells us where is the region of interest that the network is focusing on when it is making a decision. So if you see here, when we applied some of these interpretability activation maps that were off the shelf, right, that were already proposed and were being used by other AI models, we found out that they don't work for spiking neural networks as well, because again, they're not using the timing information. But when we use this interspike interval based timing information to build the interpretability map, you see that, like, as compared to this figure at the top row, now the interpretability maps in the bottom row are much more coherent and concisely give you this information about, okay, where is the region of interest in this case. And not only that, we started seeing that, if you do this interpretability map for different layers of a neural network, we found that the early layers focus on, let's say, like in this case, the early layer, layer 4, in case of the lion's image, is focusing on the eyes of the lion, the nose of the lion. In case of this lemon image, it is focusing on the circular edge that the lemon has, etc. So that means it is focusing on some edges or blob patterns, whereas the later layers are focusing more on the entire semantic information that is present. And this is very intuitive that, even in our visual cortex, the early layers capture more of these edge-like patterns, and it is the later layers in the visual cortex that capture the semantic information patterns. And this is what we are able to also explore with that of the interpretability tool that we have built with the spiking network. So we wanted to apply this tool in order to see why a model is so much more robust when we are building a spiking model rather than a standard model. And what we found out was that what these adversarial noises do is that they change some information in the input in a way where the model starts focusing on the wrong region of interest. So earlier, in case of an elephant or a dog, the model before the attack was focusing on the correct region of interest. And now, after the attack, it is focusing on this background area, as a result of which the model starts getting fooled and starts misclassifying the same image. So what we then saw was that when we actually did this interpretability map observation with spiking neural network, it turns out both before attack and after attack, the model is still focusing on the same region of interest. In fact, initially, the model might be a little bit confused, but over time, it gets it gets some time to compensate for its confusion, and over time it is able to come back to the original region of interest that it should have focused on. So what I'm trying to say here is the key takeaway is that when we leverage the right type of time statistics during training, the spiking networks can achieve very robust and accurate vision. So I think I have another 10 minutes. Is that right, Geeta, for our...
yeah, maybe, I don't know, 5-7 minutes, so that we have a bit of time for questions. I think that.
Yes. So what I'm going to do here is I'm going to skip some of these slides, and I want to kind of go to the hardware discussion part a little bit and then conclude. So what I'm going to say is, like, today spiking networks have evolved to a stage where we have been able to scale these models from simple convolutional architectures to transformers, right? And every time we bring in transformers, we have been able to close the gap between spiking models and the standard AI models. We've been able to develop, the ChatGPT style models with these spiking neural networks. But the problem again is that, everybody always asks me, are these models efficient? These are some papers that I have taken from prior works where they quote that their models are like, almost 10 to 100x more efficient than the state-of-the-art models. But it is very, very important to think about when you calculate this efficiency, are you calculating efficiency from a whole system perspective, or is there some missing system level behaviors? And it turns out that when some of these works have quoted these energy efficiency numbers, sometimes some of them, there has been some missing system level behaviors. And as a result of that, what we have started thinking about is, we need to start building hardware that allows us to benchmark these spiking neural networks. And we built something like a systolic array-based hardware. We have built compute and memory architecture-based hardware. We have built sparse accelerator-based hardware. And all of this is to essentially showcase how these models are efficient. What is the kind of numbers we are getting, right? Whether it is in terms of TOPS per watt, in terms of power consumption, etc. And one of the key takeaways that we have found out is that data movement is still very, very costly, even for a spiking neural network. So we really have to think about if you're doing expensive accesses to the DRAM or global buffer for the weights and membrane potential, you have to do it over multiple time steps. So that is going to give you a lot of cost prohibition. So how do you get around it is one question. And we have come up with mechanisms in order to mitigate data movements, whether we are doing precision scaling, using quantization, doing pruning, doing membrane potential sharing over time. All of these are interesting mechanisms one can go over. The other thing that we can do is eliminate data movement costs altogether by changing the architecture. Okay, so this is the architecture that traditionally your NVIDIA GPUs, CPUs, Google TPUs, everything, Intel CPUs, this is the left architecture is what we have. You have a memory that is connected to the compute using a bus. But what we are trying to think about is, can you embed your compute and memory all together? That means if you're doing dot product or these multiply and accumulate operations, everything is inside the memory. So you get rid of this entire communication. And it turns out today there are these very interesting emerging technologies called memristive architectures that allow you to do that. And you can do very efficient matrix vector multiplication processing with these memristive architectures. And lo and behold, we have actually come up with a spiking based simulator using this memristive technologies. And we have found out some very interesting results. We found out that, our energy and latency actually go down pretty much when we start using these memristive architectures. Time still plays a role. There is still that aspect of you have to process information over time. So there are ways in which you can get around the timing overhead. And the way we get around the timing overhead is by essentially dynamically activating how many time steps are required per input based on the difficulty of the input. So this is a very intuitive thing. Like, let's say, for example, if I ask you to recognize Einstein in both these pictures, you will recognize Einstein in the top picture very easily. But in the bottom picture, it will take you some more time because, you have to figure out, okay, where is he sitting? Right? So this is very intuitive, and you can do that on a spiking network. So essentially, think about it this way: in a spiking network, for easier inputs, you will infer them at earlier time steps. And for more difficult inputs, you can infer them at later time steps. And by doing that, you can actually get latency reduction that will eventually lead to energy consumption improvement as well. So all in all, this is the slide I want to end at, where we have found out that as compared to state-of-the-art models today, if we look at spiking neural networks, this is an apple-to-apple comparison where we are charting power versus TOPS per watt. So spiking neural networks on standard CMOS digital accelerators are at least 10x more efficient in terms of power, while giving you almost 2 to 3x improvement in TOPS per watt. So and when we go for something like an in-memory computing architecture, then the power just shoots off, right? So you can actually go from like a less than 1 watt range to around 10 milliwatt range with these in-memory computing accelerators. And the throughput also shoots up by almost 20x. So it really comes down to what type of hardware and what type of algorithmic philosophies can you bring in together. And all of these philosophies can really help you push to this left of the chart, which is low power and as high energy efficiency as possible, right? So this is what this is where I think I'll stop and I'll conclude and maybe open the floor to some questions.
Thank you so very much for this exciting talk about, various aspects of spiking neural networks. So I'm sure, there are many questions, and so I would now like to ask the audience, please feel free to write your questions, and then I will read them in the chat. So maybe I can just, in the meantime, ask one first question. We talk now a lot of time, about spiking neural networks. Do you see also any benefit of combining spiking networks with normal neural networks, or would you suggest to just completely, switch to spiking networks because they are better in any way?
Yeah, no, I think it's very important to start doing combinations, right? I think that is an important thing that we have also started finding out. So some of our recent works actually do have a hybrid pipeline where, let's say, for video tasks, where we are actually processing the temporal aspects through the spiking flow, and then the some of the, you still need to process that RGB image because it contains so much of dense pixel information through the standard flow, right? So we have been trying to hybridize model architectures. There are cases where a fully spiking backbone works, but those are more smaller cases, like I said, for, like, on device applications where power is extremely constrained. But wherever you think that power is not as constrained, if you can stretch the power limits from 10 watt to 50 watts, I think you can always use spiking as an enabler. And again, the idea is the enablement doesn't just come from efficiency, it also comes from the temporal processing aspects. So you might want to think about, what type of hybrid, when you build these hybrid architectures, what type of features you want to bring in.
Okay, yeah, so thank you very much. So the second question would be, so spiking networks are one step closer to the human brain. I mean, coming from normal neural networks, do you believe one could get closer to the human brain and capture maybe aspects which would make it even more energy efficient? So where do you see the future?
Yeah, I think that's a great question. I feel that more and more as we go into the future, we need to start thinking about what type of other cognitive philosophies are there in the brain, right? For example, we have not, like, we think that, like, we have been running with back propagation as a learning rule, right? But in the brain, for example, weight transport is a huge problem. Like, you don't have the same in case of back propagation, we use the symmetricity. Like, the same weights are used for forward and the backward passes, but the brain has a completely different architecture. The other thing is that in the brain, there's a lot of recurrence and feedback. And feedback is something that we don't see in our architectures at all. And I feel that there is a lot of scope by using feedback also. So we have to modify this kind of architectural style. And the reason why we have stayed away from feedback is because the way we process information, right? We don't want to get into a loop, and we want to do it as parallelly as possible. So anytime you bring in cyclical graphs, then the parallel processing suffers. But then there are ways in which you can do that as well, to come up with a trade-off between parallelization and cyclical processing. So I think we have to start thinking about all these aspects. The other side, from besides architecture, I think the learning rule can also be interesting. I mean, there's a lot of scope for behavioral learning. There is, when we talk about plasticity today in the AI models, it's very error dependent, but it's not really dependent on some kind of motivation or behavior. And as we are thinking about agentic AI, we need to start thinking about not just reward based, but also some kind of a behavior motivation based, right? Which is how the humans are as well. We are not always going after reward based learning. So I think those are the key things that we can incorporate in traditional AI models as well as in these emerging AI models using spikes.
Okay, yes, thanks so much. And so maybe another question also on the application side. So where do you see the future with applications? You showed some applications which were very intriguing, but I mean, so what would you predict there? I mean, what would be the, let's say, the large areas, for instance, robotics, I mean, where
Yeah.
these kinds of methods could make a real difference?
Yeah, I think going forward, I believe that there's a whole lot of scope with autonomy with
Yeah.
these models. Because with autonomy, you have to think about not just the processing stack, there's a sensor and the control. So the sensor has to talk to the processor, and then the processor has to talk to the control. And now the processor is where we push in the AI, right? We, of course, want the AI processor to be as efficient as possible, but you have to remember that in autonomous tasks like robots, drones, actually, it's the sensing pipeline that consumes almost more than 50% of your entire latency and energy. So that's where we can think about, can we bring in intelligence in
Yeah.
order to do data processing better, right? Right now, we are doing data analytics better. Of course, that is very good. But, as soon as we think about physical intelligence, sensing, real-time interactivity, everything becomes important. And that's where you really, and intelligence can help us there, right? Do we need all this data that all our, if you have seen a Waymo car, it has like at least 6 or 7 sensors on top of it, right? Do we need all that data is the question, right? And we need some way of intelligently processing and filtering that data out. And that's where we need low power processing also, right? Extremely low power. We don't want our sensors and the filters to take so much of energy there, which is unfortunately the case today. But I feel that those are the leaps we need to do if we really want to get to a world where we have the R2D2s and C3POs surrounding us in some way. Yeah.
Okay, and then there's another question, I mean, from the audience also. Are there any data center deployments of spiking networks in the world right now?
Yeah, so I mean, we are all like, when we think about spiking models today, we are all running on data centers. Like, I run my models on the 800 GPUs. You will get some Hugging Face models right now if you are thinking about using Spike GPT or Spike-based Llama architectures. There are some Hugging Face models, but yeah, not like spiking networks. The key application is edge. So we don't want to, the idea is that we don't want to scale them up for the heck of scaling them up, right? They are there to help you pervade towards edge applications. And that's the reason why you will see not a lot of these Hugging Face or VLAMA based or VLM based installations of spiking. But yeah, I mean, when we train our models, we still are training our models on the A100 and the H100 GPUs. But the idea is to deploy them in these extremely constrained environments. Yeah.
Okay, yeah, so our time is up. I would like to thank you again, Priya, for an exciting presentation. And I think it was a great start of our new webinar series. I think we are all looking forward to the next time. Thank you also very much to the audience for attending this webinar. And yeah, have a nice day. Thank you.
Thank you, Geeta. And it was a pleasure, really. Thank you so much again.
Thank you.
Take care. Bye.
Take care. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.